Okay, hello everyone. Welcome to today's lecture. My name is Alicia, and I'm going to be taking you guys through our 3 and 4 methods lecture for today. So our lecture is provided by ATAR Notes, which is a service for high school students. We provide study notes, lectures, discussions, videos, newsletters, the infamous ATAR calculator. I remember using that a lot when I was in year 12, articles, and heaps more. And we also provide a tutoring service by previous year 12 students called TuteSmart, study guides, and Ed Unlimited, which is a service with all of the study guides for all of your subjects in one place. So, this is our Methods 3 and 4 lecture for today. Let's get started. So, let's quickly go over all of the content that you will be going through in Year 12, Units 3 and 4, and then I'm going to go through what parts of this content we're actually going to be looking at in today's lecture. So, you have probably done most of this content at school already. In Unit 3, you've done the logarithmic function, then you've done further differentiation and applications of that. So that involved differentiation of trig functions, exponential functions, and log functions, as opposed to just polynomials, which is what we did in Year 11. And then you also looked at integration, and you would have done a few different applications of all of this calculus. So you would have looked at optimization, rates of change, and all of that kind of stuff. Then getting into Unit 4, we're looking at further functions and statistics. So we did a little bit more differentiation. Most of this involved the second derivative, concavity, points of inflection, stuff like that. Then you looked a little bit more at trig functions, then discrete random variables, then continuous random variables and an application of continuous random variables, which is the normal distribution. And then you also looked at interval estimates for proportions. So, what we're going to be looking at today are these last 3 dot points in yellow. So we're going to be going over all of these topics today. Hopefully you have already kind of started or gotten a decent way through this content at school. So some of this stuff should hopefully be a little bit of a revision for you. But if you hadn't, that is completely okay as well. I'm going to be going over everything in a really understandable way. Obviously, I studied all of this stuff in Year 12 fairly recently, so I kind of remember learning it and remember being confused. So I'm going to be going over everything in a really understandable way. Alright, so now let's go over the structure of today's lecture. So, we have a 2-hour lecture, which is recorded. So that means that you can pause at any time if you need to take a break or you need to quickly jot something down and it's taking you a bit longer than you expected, or I'm going too fast, or you just want to quickly rewatch it a few days later or something like that. Or if you're not available at the time that the lecture is starting to stream, then you can also watch it at any other time as well. But if you have any questions at all, so this includes anything about like an example that we did in the lecture, or like a bit of content that you didn't quite understand, or if you needed further clarification on an explanation that I've given, or even if you have questions about other topics in methods that we're not doing in today's lecture, say something about differentiation or integration or something like that. Also feel free to ask me any questions about any of the other subjects that I've done, which I'll go through in a second as well. And any other questions about kind of studying in general, externals, balancing all of your subjects, even uni, moving out of home, all of those kinds of things, feel free to ask any questions at all, and I'll be available to type you an answer. And then the last thing that I wanted to say is that the slides are going to be downloadable where you access this lecture. So please feel free to download those and use them later on for your revision, to pop in your notes, anything like that. Now, before we get into the content, I just want to give you guys a quick kind of rundown, a little bit about myself. Super quickly so that we can get into the content, but just so that you guys know me a little bit better. So the first thing that you guys are probably most concerned about is how I went in year 12. So I graduated in 2021. I went to a pretty small country school out in the Scenic Rim, which is in southeast Queensland if you haven't heard of it. And then my ATAR was 99.55, and my overall score in methods was 95. So a breakdown of that is I got 20 on the assignment, so I got full marks on the assignment. For the first internal exam, I got 15. For the second internal exam, I got 14. And then for my external exam, I got 46 out of 50 marks. So that's how that worked out. So evidently, I kind of got most of the marks in the internal assessment, and then I kind of lost a few more marks in the external assessment, but I mean, that is kind of to be expected. But what I might go through at the end is kind of where I feel like I went wrong, and how if you're kind of in a similar position to me where you really wanted to get a high ATAR, like a very high one, and you're not just kind of like looking to do decently well, I'll go through kind of the mistakes that I made with that external exam. Alright, and then the last thing about myself is that I'm currently a university student, so I'm in second year and I'm studying a dual degree in law and economics at UQ. Alright, if you have any questions at all about anything that I just said, I won't go over it too much more because I want to get onto the content, but if you have any questions, please feel free to pop them in the live chat. Alright, with all that being said, let's get into our content for today. So what we're going to start with is a quick review of statistics. So this is going to be content that you have hopefully studied in year 11 and potentially even year 10. Kind of simple concepts such as expected value, variance, and standard deviation. What exactly is a random variable? You know, we're studying discrete and continuous random variables in year 12, both random variables. What is a random variable? And then we're going to look at the difference between discrete and continuous random variables. This is a really important point to understand because obviously when you get an exam, say in your second internal exam if you haven't had it already, and your external exam, sometimes a question doesn't tell you whether the distribution you're being asked about is discrete or continuous, right? Sometimes it doesn't tell you, so you really need to be able to distinguish between the two. The other reason that this last up point is very important is because in some questions you're actually going to have to use both, right? The most common example of this is if you are given a few values that are continuous random variables, and you need to use this continuous distribution to find a p-value for a discrete random distribution. So, I can't quite recall if we're going to look at one of those questions today, but probably not because they are generally pretty complex. You might only have a few of them in your textbook, but they do come up. So if you would like to have a look at those, I'd recommend finding a few of those in your textbook. Alright, so let's get into what expected value is. So the expected value is what we usually call the mean of the distribution, or mu, which is a Greek letter, this kind of like long U kind of looking thing. So it is kind of the value, I mean, it is what it is. It's the value that you would kind of expect to get if you were taking a trial, right? So we can find the expected value by summing the products of each value of x and its probability. So this is the formula that we have right here. Of course, this symbol, sigma, it's an uppercase sigma, represents sum of. So what we're looking at here is the sum of x multiplied by the probability of that x value occurring, right? The formula looks a little bit complicated if you're unfamiliar with it, but once you go through an example, it really is quite simple if you're getting confused by the notation, because I know that I sometimes do as well. So, we're also able to find an expected value of a function of x. So, if we have the expected value of g of x instead of just x, like we had in our last slide, then what we can do is multiply the value of the function of x by the probability of x occurring. And we're going to go through an example of that right here. So, say our function of x, g of x, is 3x plus 1. What we're going to be doing is we're going to be multiplying 3x plus 1, g of x, by f of x to get our mean, right? Or our expected value. And then, of course, this is just our formula from the last slide, and this is just the expected value of regular x. Alright, now getting on to variance. So remember, variance is a measure of spread. So it tells us kind of how spread out the data is, right? Whether it is really closely concentrated in one spot. I'll draw a quick but terrible diagram for you guys. If it's really concentrated around one spot, it might look something like this, right? Where it's all concentrated in this one spot here, but if it is really spread out, it might look something like this, right? Again, that's a terrible diagram, not an art student. But as you can see, if it's all really close together, really compact, we're going to have a low variance because each value doesn't vary much from one another. But if it's really spread out, like if it's kind of lower and more spread out, then we're going to have a high variance because each value varies a lot more from the other ones. Right, so let's get into how we actually calculate variance. So variance is represented by var of x. We don't have a special symbol for it. And it's calculated by finding the expected value of x minus mu. Remember, mu is the mean or the expected value, squared. So this is kind of an application of our formula, this one here, where we have the expected value of a function. So our function here, g of x, is x minus mu squared. So mu is our expected value. It's going to be the number that we find using our expected value formula from here. Oh, right. So kind of expanding this out a little bit, what we're going to have is x minus mu squared multiplied by the probability of x and the sum of that. So this is how we find our variance. Now let's get on to the last measure that we're looking at, and this is standard deviation. So hopefully you've heard of standard deviation before. Remember, standard deviation is again a measure of spread. It tells us about how spread out the data is. And we can calculate the standard deviation by finding the square root of the variance. Now, really quickly before we move on to the other stuff that we have done here, I just want to make one thing clear. You are not given the standard deviation formula, this one here, on your QCEE formula sheet. So you're given your expected value formula, you're given the variance formula, but you're not given the standard deviation one. So if I were you, I would think of a way to remember this. Obviously, it's not that difficult in concept. The tricky thing is, at least for me, and I still can't remember this without thinking of my kind of the way that I remember it. I can't just remember it off the top of my head. And that is that the standard deviation is a square root of the variance, not that the variance is the square root of the standard deviation. Like I would always get confused about where the square root goes, and it's really easy to make that mistake, especially in an exam where you're just kind of like, worried about not finishing the exam on time. You want to get everything done quickly. You're just kind of writing down what you remember. So what I'd recommend is thinking of a way to remember it. So there's kind of two ways. Obviously, you can have whatever way you want, but the two ways that I remembered it was that if we have standard deviation, I'd kind of think of the S and the D and think squared. So I'd think standard deviation squared equals variance if we just took this over. That's one way that I remembered it. The other way is on your formula sheet, you're given the formula for, I believe it's for confidence intervals, finding the standard deviation for confidence intervals. I'd have to have a look again. But you're given the standard deviation formula there, and they have a square root over that. So that is another way that you could remember it. But yeah, make sure you think of a way. All right, moving on. So standard deviation is denoted by this letter here, which is a lowercase sigma, this little kind of round thing with the tail. And therefore, variance is equal to sigma squared. So we just took that surd over the other side. What you can see here is a normal distribution, if you haven't done those already in class. So this is a continuous random variable, but the important thing that we're looking at here is actually the standard deviation. So as you can see, we have our mean in the middle. This is our expected value. On either side of the mean, we have one standard deviation, plus one standard deviation, minus one standard deviation, right? And as you can see, the furthest standard deviations we move away from the mean. So here we have 2 standard deviations for the blue and 3 standard deviations for the purple, right? The further we move away from the mean, the more standard deviations we have. So this is kind of an important diagram that you're going to want to remember when we're getting onto the normal distribution and we're going over standard deviations and Z scores and the standard normal curve and all that kind of stuff. But it's just an important thing to actually understand what the standard deviation means. All right. Now let's get on to our next question in our review of statistics, and that is, what is a random variable? So remember, in year 12, we're studying random variables only. We're doing discrete and continuous random variables. So all of the statistics we're doing is covered by random variables. So a random variable is a variable whose value is unknown, or a function that assigns values to each of an experiment's outcomes. So what this essentially means is that our outcomes are a random occurrence, right? An example of this would be rolling a dice 3 times and finding the result. That's random, right? But an algebraic variable, such as graphing a function, is not random, because it isn't kind of dependent on chance, right? It's kind of already plotted out for us. When we're rolling a dice or picking marbles out of a bag, or any of that kind of stuff, we might be able to kind of predict what's likely to happen, but we don't know what is going to happen, if that makes sense, right? So we might be able to roll a million dice and kind of say, well, chances are we're going to get half heads and half tails, but the key point there is that we have chances are, right? If it was a non-random variable, we would be able to say, this is what our outcome is going to be, right? So our random variables are classified as discrete or continuous. So quickly pause the recording, have a think. Do you remember what the difference between discrete and continuous random variables are? Right? So discrete random variables are just essentially variables where the outcomes are discrete, right? So it just means that we can only have certain outcomes, and usually these outcomes are kind of like integers, right? An integer just is like whole numbers, right? So just going up in values of 1. So an example of this is getting 1 through 6 on a dice, right? These are discrete outcomes because you can't get 1.5 on a dice. You can't get anywhere between these values. You can only get these values. In other words, there are a set number of outcomes, right? So, here there's 6 outcomes, right? If you're picking marbles out of a bag, there might be a certain number of outcomes, so forth. However, when we're getting onto continuous random variables, these are obviously continuous. So any value but in a certain domain is possible. So we could have, not just 1 through 6, but we might be able to have 1573 point, so forth. We could have kind of any value. So continuous random variables typically are measurements, because these are kind of the things that usually can be continuous. So such as height, distance, time. You might get, say, velocity, weight, any of these kinds of things, right? So now let's get on to kind of the bulk of our discrete random variable content for today. So what we're going through today for our discrete random variables is we're going to be going through Bernoulli sequences and binomial distributions. So this is the content that is really specified in your syllabus. So we're going to be going through that now. So let's start with Bernoulli sequences. So Bernoulli sequences describe a sequence of repeated trials. So what does this mean? Right? It means that each trial must result in a success or failure. So there's a few different ways to think about this, right? It means that we must have kind of two outcomes, a success or a failure, right? An example of this might be if you are going to work in the morning and it's really cold and you have an old car or something like that, and you're trying to get your car to start, and every time you try to get your car to start is a trial. Maybe you try 3 times for your car to start, right? And you have a success, which is your car starting, or a failure, which is your car not starting, right? This can also get more complicated. So instead of just thinking of kind of this 2 outcomes, right? Sometimes you even need to broaden it a little bit. So an example of this might be if you have the classic example of a bag of magnets, and you have, say, 5 different colors of magnets of marbles. Sorry, marbles. 5 different colors of marbles in there. And you're asked, what is the probability of pulling out a red marble, right? So even though there's 5 possible outcomes, because you could pull out 5 possible colors, right? You still have a success, which is pulling out a red marble, or a failure, which is pulling out any other color. So you also need to consider that when you're thinking about what is a Bernoulli sequence. Our next rule is that the probability of success is constant for all trials, right? So this means that the probability of succeeding doesn't change. An example of this might be if we're going back to our starting our car example. If, for example, maybe your car is more likely to start the more times you try to start it, because it's kind of warming up each time you start it, or something along those lines, that means that we wouldn't have a Bernoulli sequence, because the probability of success of the car starting is not constant for each of the trials. It's changing, right? Our last rule is that the trials are independent. This is really important too. It means that a previous trial is not impacting the following trial. The classic example of this is, again, if we have our bag of marbles. If you're pulling out 3 marbles, right, but you're not putting them back in every single time you pull one out, the probability of pulling out each color is changing. So say you pull out a red marble to begin with and you put it down, you don't put it back in, there's now less red marbles, or a smaller proportion of red marbles and a larger proportion of other colors of marbles compared to your first trial. So now you have a smaller chance of pulling out a red marble again. So this means that our trials are not independent. So independent trials are always going to have what we call replacement, which means every time you kind of, take something out, like a marble or a card out of a deck or something along those lines, you're always putting it back in, right? The one kind of caveat to this is when you are looking at, I guess, kind of continuous random variables in conjunction with Bernoulli sequences, right? So sometimes, and again, these are the complex questions, so like I'm not going to be going over this too much today, but just kind of if you are like more of a determined student, you might want to look into this yourself. If you're looking at a question which combines continuous and discrete random variables, you might have a scenario where you have, kind of a large quantity of objects. You might have like a barrel of 2,000 apples or something like that, and where you're kind of combining those two continuous and discrete random variables. You might have a case where like you're not, you're pulling apples out and you're not putting them back in, but at the same time, it's kind of, there's 2,000 apples, so the trials are still kind of treated as independent for our purposes in year 12, because there's so many apples in there that the proportion isn't really changing, even though you're not putting them back in. So again, if you're more of a determined student, I would look into that as well, but we're not going to be going over it today because it's more of an advanced concept. All right, The last thing I want to go over for this slide is that for our Bernoulli sequences, our probability of success is given by P, and our probability of failure is given by 1 take P. We can also write this, sometimes you might come across it as Q, right? So, obviously, our probability of failure is 1 minus P, because of course our entire probability of any outcome occurring is always 1, right? You know, you might have a 30% probability of the car starting, and that means you have a 70% probability of the car not starting, right? All of our outcomes always are going to add up to 1. So, of course, our probability of failure is always just going to be the opposite of our probability of success. So that's where that comes from. All right. Now let's go through a quick test. What I would like you guys to do is pause the recording, have a look through this, and determine for yourself which of these are Bernoulli sequences. Alright, so our first one is tossing a fair coin a few times. So this is a Bernoulli sequence because we have a discrete random variable. We have kind of two outcomes. We have a success and a failure, heads and tails. And our trials are independent, right? Our next option is trying to score a goal multiple times. So this is also a Bernoulli sequence, right? Or we can treat it as a Bernoulli sequence. So it's discrete. You can either score the goal or not score the goal. We have a success or failure situation. We don't have multiple possible outcomes. And presumably our trials are independent as well. I mean, I guess you could argue that, you know, the chance of scoring a goal is going to change depending on how you're feeling or, you know, where you are on the field or, you know, other things like that. But for our purposes, we can just treat it as a Bernoulli sequence. Our third option is selecting people at random from a high school grade and noting their age. So this is obviously a random variable. However, it is not discrete because age is a measurement, right? So somebody can be, you know, 15 years old, 3 months, 4 days, you know, 6 hours and 14 seconds old. You know what I mean? Which means it's a continuous random variable, so it's not a Bernoulli sequence. Have a quick think about if we were given this information for part C, how could this question be changed to make it into a question where we would apply Bernoulli sequence maths? Pause the recording, have a think about it. So, what a question could ask, so that we would have to use Bernoulli sequence maths, is ask, you know, what is the probability of somebody being, you know, 13 years old, of course, if we're just considering like just years instead of, you know, months and days and so forth, and not any other age at all. That is a situation where you might be using Bernoulli sequences. But again, it's kind of a gray area and you really do need to think about it, and it will definitely depend on the question. All right. So this is how we represent our Bernoulli random variables. So of course we're going to have y, and the value of this of a failure is going to be 0, and this is going to be 1 minus p. The value of a success is going to be 1, and that's the probability of that is going to be p. Now let's get onto our formula for calculating the probability of a particular outcome. So, going back to this slide, if I asked you, say, what is the probability of getting heads 2 times when tossing a coin 3 times? So tossing a coin 3 times, and I say, what is the probability of getting 2 heads? Right? We are kind of asking probability x equals 2. What's this? Right? This is the question, this is kind of the most basic question you're ever going to come across for this topic. So if you get this kind of question, what you need to look at is our Bernoulli sequence formula. So we'll get into it in a second, but let's start with kind of each element of it. So the first element is our combinations, right? So what you will see in your formula is these brackets with n on the top and r on the bottom, right? This is what you see at the beginning of your binomial formula. So students sometimes get confused about how you actually calculate this and what it even means. This is actually combinations math. So if you're in specialist, you would have gone into a lot more detail on this in year 11. But if not, that's completely fine. You don't need to worry about it. We have a formula for calculating combinations, right? We also have a way of doing it using Pascal's triangle, which in my opinion is kind of easier. And then you can also do it using your calculator very easily. So I'm going to quickly go through the formula that we have here. So what we have here is n, and now this exclamation mark is what we call in maths a factorial, right? Factorial, factorial. So what this means is that we are multiplying that number all the way down to 1. So an example of this would be 4 factorial. 4 factorial would be 4 times 3 times 2 times 1. And then 7 factorial would be, have a think about it, pause the recording, do it yourself. 7 factorial would be 7 times 6 times 5. Can I count? No. 6, 4, 5, 4, 3, 2, 1. Right? So those are what our factorials are. So not too difficult to apply, but just something new that you likely haven't seen before. So this formula is not on your formula sheet. So what my recommendation is if you did not do specialist, I would recommend not using this formula just because it's just something else that you have to remember. And in my opinion, Pascal's triangle is kind of way easier. But again, if you learn how to do it using Pascal's triangle and you're really confused, then go back to the formula, right? So these are kind of our two methods for calculating this NR without a calculator. So, as I said, in my opinion, using Pascal's triangle is a lot easier. So what you want to do here is use Pascal's triangle, so you can just quickly remember how to draw out Pascal's triangle. Remember we have 1, 1, 2, 1, and so forth. So what we're doing, that's not right. What we're doing is adding the previous two terms to get to our next term. So 1 plus 2 is 3, 2 plus 1 is 3, 1 plus 1 is 2, and you can draw this on forever. So what we are doing is using Pascal's triangle. I'll do the last row down here. Using Pascal's triangle to actually find our n combination up here. So again, I would definitely study this in more detail. I'm just going over it quickly now in case you have forgotten it. So what you need to do is use this, right? So we're going to have n rows and the r position, right? So as an example of this, if we had 3C2, what we need to do, we can either use our formula, right, and we can have 3 factorial over 2 factorial, 3 minus 2 factorial. Or what we can do is go to the third row of Pascal's triangle. So our third row is going to be here, right? To know which row of Pascal's triangle you're looking at, what you want to do is look at kind of the starting number. So our third row, we know it's our third row because this number, our second number along is 3. So down here, this is going to be our fourth row. This is our second row, and so forth. So you want to look at this number here, and you're going to start with that row, and then you're going to go to position R. So our R value here is 2. So we want to go to the second position, right? So we're going to go to our third row and then count over to our second position. So the one kind of quirky thing to remember here is that with Pascal's triangle, we start at position 0. So this 1 here is actually the 0th position. Then this 3 is our first position. First, 0th. And then this is our second position. So this is going to be equal to 3, right? Because this is our number here. So going to our third row, our second position, the number is 3. Again, that was a very quick rundown. If you are left confused by that because you didn't go through it in enough detail in class, I know a lot of schools kind of don't. Don't worry. Either kind of go and watch a video about it on YouTube or something like that, or just make sure you do a lot of practice. I won't go through it anymore today just because it is kind of more of a, I guess, like a base level concept, and I want to focus more so on like the actual concepts in the maths and some more examples. But yeah, definitely go and do some more work on that if you're feeling a little bit confused. Just remember, using Pascal's triangle, what you want to do is go to the nth row. You know what row it is by looking at the number that it kind of starts with. And then you want to go to the rth position. So the 1 is always the 0th position. So always starting with 0 and then moving it across from there. So in 3 combination 2, which we just did, we went to the third row, which was here. Then we went across to the second position. So we went to the 0th, first position, second position, and the number that we landed on was 3, meaning that our answer here is 3. All right. And then there are also a few other things you need to remember about Pascal's triangle. And these that you need to remember are primarily for more complex questions. So these are going to be for ones where you need to find the n value. So we haven't gotten into that yet so far in our lecture today, but jot these down if you haven't already. So a lot of questions are going to ask you to just find, like, what's the probability of getting 2 red marbles, something like that. But in some questions, they're going to ask you, how many trials do we need to conduct to guarantee a certain probability of getting 2 red marbles? So, if we want a 90% probability of getting 2 red marbles, how many trials we need to conduct? So where n is our unknown instead of the probability, what you're going to need to remember is these combinations, right? Because you don't know what n is. So you're going to have like n, you might have 1 or n0 are the most common ones, right? So obviously without knowing what row it is, you need to be able to figure these out, and you can't put them on your calculator because you can't just put like n on your calculator. Your calculator does not know what that means. So what you need to remember is that looking at any row, our first position for n1, our first position is always just the number of the row. So for our second row, the first position is 2. For our third row, the first position is 3. For our fourth row, the first position is 4. So for this one, this is always just going to be equal to n. And then our 0th position for any row is always 1, right? 0th position, 0th position, 0th position. Always 1. So just jot these two down. Jot these two down in your notes and make sure that you remember those. Again, for questions where n is your unknown value. Alrighty. Again, if you're confused about what I'm talking about there, just jot them down and I'll give more of an explanation when we get into those kinds of questions. I just wanted to mention it now here that we're doing Pascal's triangle. Alright. And then, of course, if you need to find a combination when you are in a calculator exam, usually you don't need to because you're not even using the formula. You're actually just using like, BPD or like stat or something on your calculator. You're just kind of popping the values in. You're not using the formula. But if you do, there'll just be a certain few buttons that you need to click on to get to it, depending on what brand your calculator is, what model it is. Usually you need to go to your usual menu, run, and then go into like options, probability, and then combinations or something kind of along those lines. But make sure you figure that out before you get into your exam. Alright, so this is the formula here for our Bernoulli sequences. So this is the combination section that we were going on about just there. So remember, to find the probability of x, we're going to have the number of trials x for our combinations. P, remember P is the probability of success, to the power of x, and then our probability of failure, which is 1 minus P, to the probability, to the power of, that should be n minus x, sorry, to the power of n minus x. Right. And then this down here is just our formula for combinations for this first part up here. But as I said, use Pascal's triangle if you're comfortable with it. In my opinion, it is just far easier. What we have here is just kind of a quick example of why this binomial probability formula works, right? So, if you have a look here, we have rolled a dice 3 times, and we have let x be the number of 3s observed. So, where t means we got a 3, and n means we didn't get a 3, you can kind of see on the table on the right hand of the slide how this worked out for us. So, as you might expect, the probability of rolling 3 threes, as you can see up the top, is going to be the probability of rolling 1 3, which is going to be 1/6, right? Because we have like 6 numbers on a dice, and one of those is 3, to the power of 3. And the probability 2 3s, right, is encapsulated by these 3 different outcomes here. So you can get a 3, and then not a 3, or a 3, then some other number, then a 3, or some other number, then a 3, then a 3. So these are the 3 kind of possible ways that we could get 2 3s, right? Then for each of these, of course, x is equal to 2, because we have 2 3s. And then, of course, for each of these outcomes, right, the probability of each of these outcomes occurring is going to be 1/6 times to the power of 2, right, because we have a 3 and a 3, so the probability of getting a 3 is 1/6, so we're going to have 2 of those, and then 1 failure, because we're going to have one number other than the 3. So the probability of each of these outcomes occurring is this part on the purple here. Now, of course, because we have 3 of these separate outcomes, we have TTN, TNT, and then NTT, we're going to have 3 of these altogether. So as you can see, this pattern continues. So for these top and bottom ones, where the order, or we can only have one outcome, right? Because we have TTT or NNN, right? We don't have a number out here, we just have 1, because there's only one outcome. But where we have 3 outcomes, we have a 3 out the front. So, what this essentially shows is our Bernoulli sequence formula. So as you can see here, we have P to the power of our number of successes, R, and then Q to the power of n minus r, which is going to be 0, right, because all of our outcomes are t. So this is, of course, 1, so we just have p to the r, right? And our combination is C3C, which is just equal to 1. And then in our next row, we have C3, we have 3C2, right, which gives us 3. So as you can see, our combinations, our combinations determine the number out the front, and the reason why the kind of our combination number increases in the middle here is because this is when we have multiple outcomes, right? So again, this isn't something that you, I guess, need to kind of memorize. It's more just to help you understanding with how our formula actually works and like why it works, right? All right. So let's get on to a simple example. So here we need to find the probability of obtaining exactly 3 heads when a coin is tossed 6 times correct to 3 decimal places. So let's have a think about what information we know, right? So we want the probability that x equals 3, because we want the probability of obtaining exactly 3 heads. The coin is tossed 6 times, so we have 6 trials. And let's think about our probability of success and our probability of failure, P and Q. So P, probability of obtaining 1 head, is going to be 1/2, right? Because it is a regular coin, right? And then of course Q is going to be 1 minus P, or also 1/2, because that's going to be the probability of getting tails. Alright, so let's go through our actual our answer. So as you can see, popping in all of those values into our formula, right, we are going to have n, which is 6, r, which is 3, and then p to the power of r, so 1/2 to the power of 3, multiplied by q to the power of n minus r. And this gives us 5/16. One more other tip that I would have you to make sure that you are familiar with multiplying fractions, right? Because of course, obviously, if you are doing this without a calculator, which you most likely will be, if you're using the formula, then you want to make sure that you are able to apply our power to each of the brackets and then multiply. So remember, just as a quick reminder, if you want to multiply two fractions, say A on B and C on D, all you need to do is combine the top and combine the bottom. So you're going to get AC on BD, right? And that's all you need to know. And then of course, if you have a fraction, say m over n to the power of a, remember that power is just applied to both terms. So m on a and n on a. So just some simple index laws, fraction stuff you would have learned in year 10 or year 11. Alright, now let's get on to kind of the relationship between Bernoulli random variables and binomial distributions. So, remember, a Bernoulli random variable is where we can describe the outcome from a Bernoulli trial, right? So if x is the number of successes in n Bernoulli trials, each with a probability of success p, it's essentially just saying if we just have our Bernoulli trials, our Bernoulli sequence, right, with x, n, r, p, the values we've been learning about, this means that we have a binomial probability distribution. So a Bernoulli sequence is going to have a binomial probability distribution. What does this mean? Remember, a binomial is where we have two numbers, right? Binomial. So I'm going to show you what this looks like, right? So the binomial probability distribution is different for values n and p. Right? So the probability of guessing MCQ or multiple choice questions with a success rate of 0.2 and 0.5. So as you can see here, the probability of guessing multiple choice questions with a success rate of 0.2 is here, and 0.5 is here. So, now we want to get into how to calculate the expected value and variance for binomial random variables. So, it's a similar concept to what we went over with our statistics revision, but it's a little bit easier here. So for our expected value, all we need to do is multiply the number of trials by the probability of success, n by p, and our variance is going to be np, or our expected value, multiplied by our probability of failure, or q, or 1 minus p. So, these are on your formula sheet, and you don't really need to worry too much about how they got it, but you might be able to recognize some similarities between these formulas and the ones we went over at the beginning of the lecture. So, in a quick example here, if we have a test with 50 multiple choice questions, each with question having 4 possible answers, a student guesses the answers to all questions, let x be the number of correct answers. Again, pause the recording, have a go at this yourself before you go over the answer. Our first question is, how many will p be expected to get right? So we want to find the expected value. Remember, this is a binomial distribution, right? So we know that our expected value for a binomial distribution is going to be equal to np. Our number of trials is 50 because he has 50 opportunities in every single question for a failure or success, right? So our failure is getting the wrong answer, success is getting the correct answer, so he has kind of 50 opportunities to either get the wrong or right answer. And then p is going to be 1/4. Right? Because we're asking how much is he expected to get right. If there's 4 answers to each question and he's just guessing, he has a 25% chance of getting And then to find the variance, remember our variance for a binomial distribution is equal to NP 1 minus P. So we'll just apply the formula from here, and I'll show you guys the nice typed of answer. So of course, applying our formula, we're going to get 50, which was 50 multiplied by a quarter, which was our NP from up here, multiplied by 1 minus P. So 1 minus a quarter, which is 3/4, and this gives us 75 on 8. Again, make sure you're practicing with multiplying those fractions together so you can do this kind of stuff without a calculator. Alright, our next section is on finding the sample size for a binomial distribution. So, this is going back to what I was talking about when we were going over Pascal's triangle, and I was kind of saying this is what you need to remember if you're ever asked a question where n is your unknown rather than the probability. So, as I said before, make sure you jotted those Pascal's triangle rules down, and then we'd explain more of the context when we got to this section. So, finding the sample size questions are kind of common, complex, familiar type exam questions, maybe even complex, unfamiliar if they add a level of complexity to it. What you'll typically be asked in these questions is what does n need to be for our probability to have this, to be this certain amount. So, for example, how many lotto tickets to buy to ensure a 95% probability of winning. Right? So, in these questions, what you're going to know is you're going to know P. That's going to be known. Right? You're going to know the probability that x equals or like is greater than or less than or so forth. A certain value, you're going to know that. What you're not going to know is n. You're going to need to find n. So for these questions, what you need to do is apply your binomial probability formula, right? So you're going to have probability that x equals r, and then you're going to have your formula, n, r, p, so forth. That stuff we were doing before, right? So that's what you want to apply here. Of course, you're going to know your probability, you're going to know your p-value, and then what is going to happen, and we'll go through an example of this, but what is going to happen is most likely you're going to be able to get rid of this n here, right? Because obviously we have kind of two n's. We have the n here and the n here in our formula. So chances are you're going to be able to get rid of the n here by applying those rules that I was talking about when we were going through Pascal's triangle. And what you'll end up doing is solving for the n up here. So get rid of this n, then your only unknown will be the n up here. And then what you'll be able to do from there is use log laws to solve for this n, right? Because what you're going to get is you're going to get a certain number equaling q to the n minus r. Remember, whenever you have an unknown in the exponent, or like up in the power, going back to the beginning of the year, beginning of Unit 3, what you want to do is use log laws to solve for that. So you can either pop a log on both sides, or you can use that quick little conversion, which is the first formula in your QCEE formula sheet under the logarithms heading. Again, we're going to go through an example of this in a second, just in case you're confused, but I'll quickly run over that procedure again. So remember, when you have a finding the sample size question, what you're going to have is you're going to know P, you're going to know the probability, and R, of course, but you're not going to know N. What you want to do in these scenarios is put all the values you know into our you're then going to be able to do is get rid of this combinations part by using those rules that I was talking about with Pascal's triangle, and then solve for this n up here using log laws. So let's go through an example. So here we have the probability of scoring a goal is 0.48. So I'm just going to quickly jot down the information that we know as we go through it. Remember, if you are familiar with this kind of thing or you just want to have a go, make sure to pause the recording and have a go. But I'll just go through the solution now. So we know that from this, P equals 0.48. What is the least number of shots that must be played to ensure that the probability of winning at least once is more than 0.95? So, we know that the probability of winning at least once, we want this probability to be more than 0.95. So what we need here is a strict inequality. If you're unfamiliar with what that means, a strict inequality is these ones, where we don't have the equal sign as well. And then kind of a regular or like a weak inequality is where you have these ones. So because our probability needs to be more than 0.95, it can't be equal to 0.95, it has to be more. We need that strict inequality. And then we'll get on to the second part in a tick. So let's start off with this first part here. So of course we know this is a finding sample size question because we know we're given P, we're given the probability, we're given R, but we don't know N. What is the least number of shots that must be played? This is N. What is N? Right? So remember what we want to do is you want to apply our binomial probability formula. Now, there is actually a trick to this that you need to make sure that you remember for these questions. So, starting with what we had up here, we want the probability that x is greater than or equal to 1, and this probability needs to be greater than 0.95. Alright, so let's just say that we apply our binomial probability formula, like our NR in brackets, and then our P to the R, and our 1 minus P to the N take R, that stuff, right? Say we apply that, and we just put it, in here. So we want the probability that x is greater than 1, so we're going to need to start with probability that x is 1, and that's to be greater than 1, so we need to go probability that x equals 2, and then 3, and so forth. So we kind of don't really have a limit here to all of these probabilities that we're putting in. We don't know yet, right? So, of course, we don't know the limits, we can't physically do this, and also, even if we did know the limit, we wouldn't want to put in a bunch of these separate formulas, right? It would just take way too long, it would be way too much effort, we want to avoid effort, right? So there is actually an easier way to do this, which I'm sure you can see already, and that is to use our 1 minus trick that I have right here. So, remember, usually when we are finding probabilities, if you kind of have this probability where you have x being greater than 1, you can just consider that this is going to be equal to 1 minus the probability that x is equal to 0. Because if x is greater than or equal to 1, the only other thing that it can be is 0. And our total probability, remember, is always 1. So, if we apply this, this means that we only have to put in our binomial probability formula for that one probability, x equals 0. And this makes things a whole lot easier. So make sure that you remember that, right? When you're applying your unknown sample size question, make sure you remember to use the 1 minus trick. Alright, moving on. So, let's get back to our first line that we have up here. So we have the 1 minus probability that x equals 0, and this has to be greater than 0.95. Right, I haven't shown the working here, but I'm just going to quickly do it off to the side here. So if we have 1 minus the probability that x equals 0, right, I'm just going to quickly pop in our values into the binomial probability formula and quickly show you how those kind of two equations that I gave you when we were going over Pascal's triangle can be applied right here. So hopefully you jotted those down. If not, we'll go over them again right here. So let's apply our formula. We're going to have n, right, which we don't know yet, r is 0 in this case, p, so p is 0.48, that was given to us in the beginning of the question, remember how we wrote it down, the probability of scoring a goal is 0.48, to the power of r, which is 0, and then 1 minus 0.48 to the power of n minus r, which is 0. So this is what we have on the left-hand side over here. Now let's just go through and simplify this. So let's start with our combination. So remember those formulas I was going through before. If you have row n and the 0th position, this is always going to be 1. And if you have row n and the first position, this is always going to be equal to n. Remember, we went through why that works with Pascal's triangle if you want to go back to that part of the recording. So, what we know that is that this is going to be 1. Anything to the power of 0 is also 1. And then, of course, we can just simplify this a little bit further. So we're going to now have 1 minus 0.52 power of n, get rid of that 0 there. And then from there, to get to this second line here, all we did is took this 1 over to the right-hand side. Alright, now let's continue on with the question. So, as I said, we've gotten to a point here where we have this n in the exponent, or like up in the power, and that's our unknown. So, remember what I said. Quickly pause the recording, have a think about it. How did I say that we could solve these? Remember, it is, I guess you can see it on the slide, but we use log laws, right? Because we have our unknown in the exponent. Going back to the beginning of Unit 3, we're using log laws. So, as I said, you can either apply a log to both sides, or you can apply that log conversion formula, which is that first formula on your QCEE booklet for logarithms. So here we logged both sides. We used log base e, which is ln, and then so we went ln, and then remember that rule where we can take the exponent out the front, and this is what we did here. So we got the n out the front, and then all we did is took that ln over to the other side and divided it. Now, one other thing that I really want to reiterate here is using inequalities. A lot of people get confused with using inequalities to solve equations. What really happens is it's quite simple in theory, but not in practice. Right? So, when you're using inequalities to solve equations instead of like equal signs, like we have here, the rule is you change the direction of the inequality if you multiply or divide by a negative. So, I'll give you a simple example off to the side here. If we had a on negative 3 is greater than 2. Solving for a here, what we would usually do is just take this negative 3 over to the other side, right? But because we are multiplying by a negative number, what we need to do is change the direction of the inequality, just like so. So we're going to get that a a needs to be less than -6. So that's how we would use that in a simple example, right? But then, of course, if you are adding or taking a negative, you don't need to change the direction of the inequality. So if we had a take 3 is greater than 2, right? We could have a is greater than 2 plus 3 without any issues at all. Alright, so that's the basic rule. That's really all you need to remember about your inequalities, right? When you change the direction, it's because you are multiplying or dividing by a negative. So, simple in theory, right? There's kind of two issues that students usually come across with using inequalities. So, the first one is when you don't explicitly know that a number is negative. So, we have a perfect example of this here, and that is what we did is we took this ln of 0.52 over to the side, right? And as you can see, the direction of our inequality changed. So ln of 0.52 is actually a negative number, and that's why we needed to change the direction of the inequality, right? So, as a rule, when you're using kind of logs with inequalities, make sure you remember this. So if you have the log of any number between 0 and 1, this is going to be negative, right? So as you can see here, the log of 0.52, because we have the log of a number between 0 and 1, that's going to be a negative number. In fact, if you pop it in your calculator right now, you're going to get a negative number. So, even though there's actually no negative there, it is actually a negative number, which you need to be careful of. So again, make note of that, right? Okay, and then of course it's not equal to. We don't have equal to in here, right? We don't have equal to because if we have the log of 0, that is not a number. We can't find that, and the log of 1 is 0. So, yeah. Alright, so make a note of that, keep that in mind. And then the other scenario that I actually had a student have issues with the other day was using the null factor theorem with inequalities. So again, this isn't relevant to this question here, but just to make a note of this, if you ever have something where you have like, x take 1, x plus 2 is greater than 0. You can't necessarily use the null factor theorem here like you would if it was equals, right? Because for this number, actually I'll change it to make it a better example. Actually, no, it's fine. For this number to be greater than 0, right, we could have that x take 1 and x plus 2 are both greater than 0 themselves. A positive times a positive is a positive number. But if these are both negative numbers, then this condition up here is also satisfied. Because if we have a negative multiplied by a negative, a negative multiplied by a negative, we also get a positive. So, again, two scenarios you need to be wary of with your inequalities is A, making sure that you're aware that a number is negative or not. So remember, we need to change the direction of the inequality if you're multiplying or dividing by a negative. Classic example, log of a number between us that n needs to be greater than 4.58. So, this is the number you're going to get. Of course, you can only have a full number of trials, right? You can't have 0.58 with a trial. So, if you get an answer that has like a decimal place, what you want to do is in your like written answer, say like n must be at least 5, right? Because we need at least 5 trials. Okay, getting on to the second part of the question. So the second part of the question asked, what is the least number of shots that must be played to ensure the probability of winning at least twice is more than 0.95. So in this scenario here, we want the probability of winning at least twice being more than 0.95. So the only difference between part 1 and part 2 is the R value. Here the R value is 1 and here the R value is 2. So let's go through solving this. It's a very similar process, but what you can see here, I won't go through this in too much detail, but what you can see here is applying the exact same process. We actually need to have 2 applications of our binomial probability formula, and we actually end up with an n here and then an n in our exponents. And the reason for that is because remember our rule n1 equals n, so this value here is equal to n. So when we have all of these n's, you actually physically can't solve this by hand. Believe me, I tried. I remember getting one of these questions in year 12, just doing it in a textbook. I tried for like half an hour to get the answer without a calculator until my teacher told me that it couldn't be done and to give up. But if you do get one of these questions, what you need to do is pop this into your calculator. You should have like a solve function. So I have a Casio. Our solve function is called solve n, and you just put the equation in. So that is what you would need to do here, and just solve it on your calculator. Another way that you could do it instead of using the solve function is actually by graphing this as a function and then finding for what values it's less than 0.05. Whichever way you prefer. My calculator is kind of old and a little bit slow, so it's usually easier to kind of graph it than use the solve function, but if that confuses you and you have like a fancy new calculator, please use the solve function. Alright, so this is it for Bernoulli and binomial, so our discrete random variable section. Now we're going to get on to continuous random variables. So what we're going to start with is continuous random variables generally, and then we're going to get on to a particular subsection of continuous random variables, which is the normal distribution. So let's get started. As you might tell, we've already used up about 2/3 of our lecture time, so we might not get to finish all of this, but hopefully you guys have had a good in-depth explanation of discrete random variables, and you know, that should be okay. Alright, so let's get into what continuous random variables are. Remember we started the lecture with this. So a continuous random variable is one that can take any value in an interval of the real number line. So essentially this just means that our continuous random variable can have any value. So remember, our continuous random variables are usually measurements, right? Such as the time taken to eat a whole pizza, which I'm sure would be more than 1 second, but kind of could be any value within a particular domain, right? It's not going to be less than 0, couldn't be, but it could be kind of any number at all So, we need a way to represent this data. So what we do is we use probability distributions, right? And this is where we're getting into PDFs and CDFs, which you might have heard of, but we'll get into. So remember, PDFs are our probability distribution functions, and CDFs are our cumulative distribution functions. So, in our previous content block, we went over discrete random variables, but many variables are not like this. So, let's now get into our levels of accuracy. This is kind of just a small thing you need to remember, right? And that is, if we are measuring a continuous random variable, the probability of getting one very, very specific value is incredibly low, right? So it's like asking, what is the probability that one person is exactly 175 centimeters tall? Exactly on the dot. Not 175.1, not 174.9999901, exactly 175. The probability of somebody being, exactly one value is very, very low because our values can fall anywhere, right? However, when we're looking at discrete random variables, you say the probability of pulling out exactly one red marble is just, going to be a decent amount, right? Because our outcome can't be anything. It's a discrete. So, when we're looking at continuous random variables, you are always going to be asked to find the probability for a range of values. So you're never going to be asked what is the probability that something is equal to something. You're going to be asked what is the probability that our value falls in between certain two values, right? So, as you can see, say in this diagram here maybe, for example, if we are considering this curve here, the probability that your height is exactly 175 might just be like this sliver here. It's supposed to be straight, but that sliver there, right? And obviously remember, hopefully remember from school, the probability is our area underneath the function. If you don't remember that, that's okay, we'll go into it in more detail later. Remember, our probability is the area underneath the function. So if we just have a tiny sliver of width, basically nothing, because it's just 175, that area is going to be pretty much just 0, right? So that's why we're always going to be asked to find a range. Alright, now what we're going to do is get into a little bit of work with PDFs. So, remember, our PDFs are our probability density functions. So our PDFs are useful for finding probabilities, right? So you can find the probability that x is going to fall in between two values by using our integration to find the area under the curve. This should be pretty familiar to you. Just as a quick example here, say we have our probability density function that looks like this, and if this is 0 on the x-axis and this is say 10, the probability that x falls in between say 2 and 6 is going to be the area between 2 and 6 underneath here. So what you would need to do is find that area using our integration calculus. Right, let's get into an example of this. Right, so what we have here is firstly our probability density function. So we have 1.5 by 1 take x squared for x is between 0 and 1, and then 0 for all other values of x. Right? The first thing that we need to do is sketch the function of f of x. So, remember, when you're given your function with this kind of like curly bracket, that means you're going to need to draw like separate parts of the function. What I'm going to do is just draw our function kind of quickly and roughly, just so you understand what I'm talking about here. So, of course, our function is going to be negative 1.5 x squared plus 1.5 between 0 and 1. So I just expanded that 1.5 throughout the function. This is just a fairly simple quadratic. We have a negative coefficient of x squared, which means we're going to have a frowny face quadratic. So our y-intercept is going to be when x equals 0. So our y-intercept is going to be at 1.5 up here. And our x-intercept is going to be when y is equal to 0. So all we would need to do is solve this equation as a quadratic. Quickly solving this, right? All we're going to need to do is just factorize out that 1.5 again, and that's going to, of course, cancel out. So we're going to get that 0 is equal to 1 take x squared. X squared equals 1. X is equal to plus or minus 1. So remember, 1 squared is 1, and then negative 1 times negative 1 is also 1. So that's why we have that plus or minus there. That's another thing to make sure you're looking out for. Whenever you're solving anything with a squared, like we have here, x squared equals 1, you'll come across this in all areas of methods. Make sure you're always remembering that plus or minus, because it can be lethal if you forget it. Of course, our function is only graphed between 0 and 1, so we don't need to consider this negative 1 intercept, only our 1 intercept, and that's going to be there. Right. So I'll quickly just get rid of this. And then with that information, we also know that, of course, our curve, and this is just something I guess you would learn just from a little bit of experience, because our curve doesn't have a b value, so usually we have ax squared plus bx plus c for our parabolas. It doesn't have a b value, like we never have like a something x, right? That just means that it has been moved upwards, but it hasn't been moved like to the side. It hasn't been moved horizontally. So that just means our curve is going to look a bit like this, and it's not going to be kind of like, it's not going to have its peak up here or anything like that. Right. So, another way that you could figure that out is, of course, because our intercepts are at negative 1 and 1, right? You know that it has to be, like, symmetrical, if that makes sense. That's another way you could figure that out. Alright, of course, the other part, so we graph that between 0 and 1, our graph is equal to 0 everywhere else. So we're just going to draw a straight line along the axis to represent that 0. Alright, so this is our function graphed. Now let's get on to the second part of the question, which is to show that our function is a PDF. So, whenever you are asked to show that a function is a PDF, or alternatively, this is not what we're asked here, but just as another case where you need to use a similar kind of maths, is whenever you're asked, this function is a PDF, find a certain value. So this might be if you have, you're given a function, and instead of being given like 1.5, it's an unknown number that you don't know yet. find A. So in both these types of questions, where you need to prove that a function is a PDF or you need to find an unknown given that it's a PDF, you need to kind of remember these specific conditions to solve. So the first one is that the area of a PDF is always equal to 1. So the area in here of the PDF is always equal to 1. And the function itself is always positive, right? Which means it's always going to be above the x-axis. It can be negative over here. It can have a negative x value, but it can never have a negative y value. So it can never be down here, essentially what that means. So those are the two conditions of a function being a PDF. So what we're going to do is go ahead and apply those. So check the two conditions. Firstly, our function is greater than or equal to 0 for all x, so that's satisfied. Secondly, the area underneath the PDF is 1. So what we did here is we used our integral calculus to find the area underneath the function. So we went between 0 and 1, right? And we popped in our function's values, and this is of course a definite integral. So all you'll need to do here is solve this integral and show that it's equal to 1. I won't go through it now just because it's pretty simple, but that's all you would need to do there. For the third part of the question, we needed to find the probability that x was greater than 0.5, where the random variable x is a probability density function f. So we just need to find the probability that x is greater than 0.5. Remember, whenever you're finding a probability using a PDF, all you need to do is use the interval. You want to find the area underneath the PDF for that interval. So 0.5 is here. The probability that we're looking for when x is greater than 0.5 is going to be this area in here. Right? So this is going to be, of course, just looking at the graph, between 0.5 and 1 for our function 1.5, 1 take x squared dx. And then the area of this, of course, is going to give us our probability. Remember, whenever you're finding a probability, always make sure to check that the answer that you get is between 0 and 1. If you get a probability being equal to like 2.5, you know you've gone wrong somewhere because a probability value always has to fall between 0 and 1. Alright, now let's get on to the mean and median of continuous random variables. So remember, the mean, mu, or the expected value is actually defined by this formula here, which you actually have on your formula sheet, so you don't need to worry about remembering that one. And this is between a and b, or in other words, negative infinity and infinity. And then x multiplied by the function, the PDF function. Right? So we'll go over an example of this in just a second. But what this essentially means is if you're given a PDF and you need to find the mean, you want to find the area in between the domain you've been given. So you'll be given domain for your PDF. And then you just want to pop in your PDF function that you're given and then just chuck an extra x on the end and then find that definite integral. So we'll go through an example of that in a second. To find the median, what you want to do, remember median is like the middle value. Hopefully you remember that from like year 10, year 11. So what you want to do here is between the limits negative infinity, or just kind of like the lowest value of your domain, and m, where m is the unknown that we're trying to find for our function, is equal to a half. So what we're essentially saying is that if you have a PDF like this, our median value might be here. We're saying, look, we want to find the value for which, between negative infinity and m, this area is equal to 0.5, because we want the middle value. Of course, it's fairly self-explanatory. fairly self-explanatory for that graph that I showed just there because it was symmetrical, but in like others where they're not symmetrical, of course you can't just kind of look at it and know. Alright, getting on to percentiles. So the qth percentile is found using this formula here. And before I get into this formula, I just want to quickly explain what percentiles are if you're unfamiliar. So, essentially when you say the something percentile, so as an example, the 75th percentile, what you're saying is the 75th percentile, or the value at which kind of 75% of the values have occurred. So if I draw a quick diagram, our 75th percentile would be about here, because by this point, 75% of our values have occurred. Right, going left to right, 75% of our values have occurred. Our 25th percentile, have a think about where this would be? It would be here, because this is where 25% of our values have occurred. And then of course, because we're working with PDFs, and the area underneath a PDF is always 1, 75% is always just going to be 0.75, right? The 25th percentile is going to be 0.25. So, essentially what we are saying with our formula is, okay, if we're starting right at the left, negative infinity, and going up to a value p, so this would be p here for the 75th percentile, this would be another p here for the 25th percentile, and then letting that area equal whatever percentile it is for our function is going to give us like the value at which we've completed 75% or 25% or whatever of our area. Alright, so let's get on to a quick little example. Here we have our PDF half x with the domain 0 to 2 and 0 everywhere else. So we know that this is a probability density function. The first part of our question asks to check that the above statement is true. Remember, whenever you're given a question to either A, check that a function is a PDF, or B, find an unknown given that the function is a PDF, you always want to apply your two requirements, have a think about what they are. The first one is that your function always has a positive value, f of x is always greater than or equal to 0, and that the area underneath the PDF is equal to 1, exactly. So, we're going to go ahead and apply those principles to prove that the function is a PDF. And then we need to find the mean and median. So we're going to apply our equations that we went over in the last slide to find those. So, for the first part, we're just going to do our integral. So our domain is between 0 and 2. For our function, we prove that definite integral is equal to 1, and therefore it's a PDF. And then of course half x between 0 and 2, right, just kind of looks a little bit like this. So between 0 and 2, that function is above the x-axis, so it's a PDF. To find our mean, remember our formula is between a and b, or just like the limits of the domain, between x multiplied by our function. So our domain is 0 and 2. We have our function, half x in there, and as I said before, you're just going to chuck another x in there, and then find that definite integral. So we'd be finding the definite integral of half x squared. And this gives us our mean of 403. Then we need to find the median. So remember, to find the median, we're going to start right and left at negative infinity, or at the lowest domain. M is our upper limit, where we are finding m as an unknown, popping our function in there, and then letting that equal a half. So applying this, we have between 0, because that's the lower limit of our domain, up to m for half x solving this definite integral for m, we get that m is equal to root 2. Alright, now getting on to measures of spread. So we have two common measures of spread: variance and standard deviation, and interquartile range. So these have the same mean and median, but are completely different. So let's get into an application of standard deviations. So in general, for many continuous random variables, 95% of our values fall within 2 standard deviations of the mean. So what that looks like visually is if we have, oh, that was terrible. Give me a second. Okay. If we have our probability density function, right, and this in the middle here is our mean, 95% of our values are going to fall within 2 standard deviations. Right, so for each one of these green bars is a standard deviation, and this green area here is 0.95. You can see that 95% of our values are going to fall within 2 standard deviations. So on the left-hand side we have 2 standard deviations less than the mean. On the right-hand side we have 2 standard deviations more than the mean. Alright? So this is particularly applicable when you get into the normal distribution. So the PDF that I've drawn us here is a normal distribution if you aren't familiar with it already. And then our interquartile range is the range of the middle 50% of the distribution, and it's the difference between the 75th percentile and the 25th percentile. Right. So let's get into an example here. If for this PDF we want to determine the interquartile range for 2x between 0 and 1, what we want to do, so we know the interquartile range is the difference between the 25th and 75th percentiles, so of course we need to find the 25th and 75th percentiles in order to find the difference between them, right? So let's start with finding the 25th and 75th percentiles. Remember, to find a percentile, what we want to do is pop our function in the integral, start at our lowest domain value, so here it's 0. Of course in the formula it's just negative infinity, but that just means start with the lowest domain value, so here it's 0. Go up to our unknown a, and then let it equal to the percentile number. So for the 25th percentile, remember we're going to convert that into 0.25. 75th percentile, 0.75, and then solve that for a. So doing so here, we get that a is equal to 0.5 for our 25th percentile, and b is equal to 0.866 for our 75th percentile. So our interquartile range is going to be the difference between them, so we're just minusing one from the other, and this gives us 0.366. Alright, now let's get on to CDFs, or in other words, our cumulative distribution functions. So, I want you guys to have a think about and remember, if you've learned it in class, what is the relationship between a PDF and a CDF, and how do you get a CDF from a PDF? How do you start with a PDF and get up to a CDF, and how do you start at a CDF and get to a PDF? So, have a think about it, pause the recording. So, our CDF is the integral of our PDF, right? and it gives us the probability that random variable x takes a value less than or equal to x, right? So as you can see here, in this top graph we have our PDF, in the bottom graph we have our CDF, which is the integral. If we find a value, say we find this value here, right, and this point, remember we're not finding the area when we're using the CDF, we are finding a value. We're subbing in x and finding capital F of x. Remember, the capital F represents the CDF and our little f represents the PDF, right? Because we're kind of saying, like, you know, the CDF, because it's the integral, is like the parent. It's like bigger. It's like the big F. If that makes sense. So, if we are finding the function of x at this value here, what you're finding is the probability that x, big X is less than that value, right? So, to find a CDF from a PDF, what you need to do is you need to find the definite integral, and this is a little bit confusing. You need to find the definite integral of the PDF, right, with the lowest domain value, so here C would be 0, with x as the upper limit. So if you're finding a CDF, what you're actually doing is you're finding a definite integral, which usually, right, gives us a number, not a function. But when you're doing this, when you're finding a definite integral, you need to sub x in, like, just, you know, as a regular number, you know, because we're actually just putting x there. We're not like saying, you know, x represents a number or something. We're just actually putting x actually in there, right? So when you find your CDF, you're going to be using a definite integral, and you're going to end up with a function instead of a number. So this is why I say it gets a little bit confusing, because typically what you learn when you do integration is that, like, a definite integral gives you a number, and an indefinite integral gives you a function, but here it's actually a little bit mixed up. Alright? Okay. So, now let's go through some important properties of CDFs. So, first, the probability that x takes a value less than c is 0. In other words, c, which remember is our starting value here, c, is the beginning of the function. The probability that, you know, anything is happening that x is being one of these values, nothing, 0, right? Second, the probability that x takes a value less than d is 1. Right? So d is our end value. Right? So d might be a value up here. Right? So our third requirement, this one is a little bit more confusing, is that if we have x1 and x2 being values where, like, x2 is bigger than x1, like x1 is our starting one, x2 is our bigger one, you know, we kind of have our, you know, if we have our graph, we have, like, x1 somewhere here and x2 like further along somewhere here, right? The probability that, sorry, this should be x1. The probability that x is less than or equal to x1 is less than the probability that x is less than x2. Right. What this means, this is a complicated way of saying something very simple. What this means, this third part, is that our CDF is always going up. It always has a positive gradient. It's never going downwards, or in other words, it's a non-decreasing function, right? So it is always going upwards. If you see a function and it has a downwards gradient, you know, like anything like this at all, or, you know, like this, and it asks, is this a CDF? You say no. It's not a CDF because CDFs are non-decreasing functions. They always have a positive gradient. So as you can see here, our CDF is going upwards, right? Alrighty. Let's quickly run over this example, and then unfortunately we won't get to the end of this lecture, but that's okay. But let's quickly run through this example. So in this one here, we're asked that the time taken to complete a maths quiz is a random variable with density function given by, and we need to find the cumulative distribution function of x, and then use our CDF that we just found to find a few probabilities. So, remember to find our CDF, what we want to do is we want to start with our lowest domain C, right? So our lowest domain here is 5, and then our top limit is x, and it's not x representing a number, it is actually x. You're writing x in there. You're going to put your function in there, and then what we're going to do is we are going to solve this as a definite integral, right? So we're going to integrate this 5 on t squared, and then pop in 5 and x. You know, usually as how you would apply your definite integrals. And this gives us that our CDF is equal to 1 minus 5 on x for the domain previously given here. Now the next part of the question is to use our CDF to find these two probabilities here. So our first one is to find the probability that x is less than or equal to 7. Remember, when we're using our CDF, we can use the value of the CDF, not the area, the value of the CDF, to find the probability that x is less than a certain value. So, to find that x is less than 7, all we need to do is find the function of 7. Pretty easy, right? And then to find the probability that x is greater than 6, this is the opposite of what we want, because usually our CDF tells us the value is less than a certain value. So what we want to do here is invert it, use our 1 minus trick. Make note of that. If you're ever asked to use a CDF to find the probability that a value is greater than something, you need to use your 1 minus trick. So then of course we get 1 minus the function of 6. Alrighty. That was all we could get through in today's lecture, unfortunately. But please remember that these slides are downloadable, so we have a bunch of slides available for you guys to look at on the normal distribution to add to your notes. I'm going through them all now. So please make sure that you go through those, add them to your notes, use them for revision purposes, really use them to your advantage. But with that being said, let's go through a quick revision of what we did today. So we went over Bernoulli sequences and binomial distributions. We went over what random variables are, how we can find our expected value, our mean, and then our standard deviation and our variance. We went over a few different types of questions, like finding an unknown sample size. Then we went over continuous random variables, we went over PDFs, CDFs, how to find the mean and the median, how to find percentiles, how to find the interquartile range. And then I just quickly have a few reminders for you guys. I didn't have a section today on study skills, but just a few tips that I learned in Year 12. Make sure to, and I know this, you'll hear this everywhere, but it really does work. Make sure you study consistently. Just do like 10 minutes a day. It really helps. Make sure you practice complex questions, please. And make sure that you don't stress, just kind of relax, and it will all come to you. Alright, thank you so much guys for listening. I hope you have a really great rest of your day. See you later.